Most people assume airplanes are painted white simply because that's the airline's branding. It seems like nothing more than a design choice. But that's not true. The color of an aircraft is actually an engineering decision, one that affects operating costs, maintenance, and even safety. At nearly 10 kilometers, 33,000 feet above the Earth, an airliner races through the sky at around 900 kilometers per hour. Yet between flights, it can spend hours sitting under the blazing sun. A dark-colored aircraft can become 10 to 20 degrees hotter than a white one. That extra heat silently works against the airplane during thousands of flights. But if color matters so much, why do some aircraft still appear in black, red, or dark blue? Today, we'll uncover why white became the global standard in aviation and the surprising laws of physics behind that decision. By the end of this video, you'll understand how one simple coat of white paint can save airlines millions of dollars while helping engineers detect dangerous damage before disaster strikes. Let's reveal the hidden science behind the world's most common aircraft color. A giant passenger jet looks almost indestructible as it slices through thunderstorms and soars above mountain ranges. But here's something most people never realize. The greatest enemy of an airplane isn't always freezing temperatures at 10,000 meters. Sometimes it's ordinary sunlight. The moment an aircraft stops moving on the airport apron, it becomes completely exposed to intense solar heat. On scorching summer days, an invisible battle begins, a battle between the laws of physics and engineering. And in that battle, the color of the aircraft suddenly becomes one of the most important factors determining reliability. The explanation begins with simple physics. Dark surfaces absorb almost the entire spectrum of sunlight, trapping heat like a giant solar collector. White behaves very differently. Instead of absorbing energy, it reflects up to 80% of incoming sunlight back into the atmosphere. That reflection prevents the aircraft's thin outer skin from turning the cabin and internal compartments into an oven. Paint the same airplane black or dark blue, and in hot climates, the surface temperature can climb to nearly 90 degrees Celsius, 194 degrees Fahrenheit, hot enough that touching the fuselage becomes almost impossible. A white aircraft, under identical conditions, remains dramatically cooler. And that temperature difference changes everything. Hidden just behind the aircraft's thin skin are kilometers of electrical wiring, delicate sensors, hydraulic systems, and highly sophisticated flight computers. These systems hate excessive heat. If internal compartments become too hot while the aircraft is parked, onboard computers may detect abnormal temperatures and refuse to allow engine startup until everything cools down. Passengers suffer too. Cooling an overheated dark aircraft requires powerful air conditioning systems to run at maximum capacity for long periods before departure. That consumes large amounts of fuel before the airplane has even left the ground. White paint dramatically reduces this cooling load, helping maintain comfortable cabin temperatures while saving both fuel and energy. In aviation, every degree of temperature reduction lowers stress on critical systems and helps ensure electronics perform flawlessly during takeoff. But protection from sunlight is only the beginning. The real story becomes even more fascinating. Modern airplanes are changing. For decades, aircraft were built primarily from aluminum, a lightweight metal that handled changing weather remarkably well. But aviation never stops evolving. In the 21st century, manufacturers quietly launched one of the biggest revolutions in aircraft construction. Instead of relying mainly on aluminum, engineers began replacing large sections of the airframe with advanced carbon fiber composite materials. Today, more than half of the structure of many modern passenger jets is made from these lightweight composites. They're significantly lighter than aluminum, yet even stronger. That means aircraft burn less fuel, carry heavier loads, and fly farther than ever before. But this incredible breakthrough came with a hidden weakness:
one that most passengers never hear about. Unlike aluminum, carbon fiber composites have an invisible enemy: heat.
Carbon fiber composites are incredibly strong, but their strength comes from more than just the fibers themselves. Think of them as thousands of ultra-strong carbon strands bonded together by specialized industrial resins. Those hardened resins are what hold the entire structure together, giving wings and fuselage panels their remarkable strength. The problem? Every resin has a thermal limit. Once temperatures rise beyond that threshold, irreversible damage can slowly begin inside the material. Unlike aluminum, which simply expands when heated, composite materials react very differently. When a dark-painted composite panel sits under intense sunlight, the bonding resin gradually softens. At high altitudes, constant exposure to ultraviolet radiation makes the problem even worse. Over time, microscopic layers inside the material can begin separating, damage that's completely invisible from the outside. As thousands of flight cycles pass, those tiny internal separations can grow, reducing the lifespan of expensive structural components and leading to costly repairs. This is exactly where white paint becomes one of aviation's greatest protectors. By reflecting most of the sun's energy, white keeps composite materials well below dangerous temperatures, preserving their original strength for years of safe operation. For modern aircraft, choosing white isn't about appearance. It's about protecting the very structure that keeps the airplane flying.
There's a common belief that dark airplanes fly less efficiently because heated surfaces disturb the airflow around them. It sounds convincing, but it's completely false. Color has virtually no effect on an aircraft's aerodynamics. The real concern has nothing to do with airflow. It has everything to do with protecting today's advanced materials from overheating. But heat isn't the only hidden cost of colorful airplanes. There's another factor most people never think about: weight. And surprisingly, paint itself can add hundreds of kilograms to an aircraft.
From a distance, an airplane's surface looks smooth and almost weightless. In reality, painting a commercial airliner is an enormous engineering project that takes place inside massive maintenance hangars. Before an aircraft receives its final appearance, technicians carefully cover the entire fuselage with multiple protective coatings. First comes a corrosion-resistant primer, then a base coat. Finally, everything is sealed beneath a durable protective finish. For a large wide-body jet, the process requires hundreds of liters of paint. Once dried, that paint forms a surprisingly heavy outer shell. And here's where things become even more interesting. Not all colors weigh the same.
The secret lies in chemistry. White paint is made primarily with titanium dioxide, one of the most effective pigments ever developed. Because it provides excellent coverage, only a thin layer is needed to completely hide the metal or composite beneath it. Dark colors tell a different story. Rich reds, deep blues, greens, and especially black often require multiple thick coats to achieve a consistent finish. Many colored pigments also contain heavier chemical compounds, making the paint itself significantly denser. By the time the aircraft is finished, the difference between a white airplane and a dark-colored one can reach 200 to 300 kilograms. That may not sound like much compared to a giant airliner, but in aviation, every kilogram matters. Aircraft engineers carefully account for every kilogram on board, because physics never takes a day off. Every extra kilogram forces the engines to burn slightly more fuel. Now, imagine carrying an extra 300 kilograms during thousands of flights every year. That small difference quietly turns into tons of additional fuel burned over the aircraft's lifetime. For airlines operating fleets of hundreds of airplanes, those extra costs quickly grow into millions of dollars. Some people believe brightly colored aircraft are easier for air traffic controllers to see in poor weather. That may have been a reasonable guess decades ago, but today, controllers guide aircraft almost entirely with advanced radar systems. not by watching their paint schemes. Saving fuel is certainly a major advantage of white paint, but its most important benefit appears only after the aircraft lands, because that's when engineers begin searching for something far more valuable than fuel savings: the earliest signs of danger.
Every time a passenger aircraft returns from a long flight, a team of maintenance engineers is already waiting on the ramp. Armed with powerful flashlights and years of experience, they inspect every inch of the aircraft. Their mission is simple: find even the smallest defect before it becomes a serious problem. This is where white paint reveals one of its greatest advantages. The bright surface acts like a giant inspection screen. Even the tiniest crack, scratch, stain, or dent stands out immediately. During every flight, an aircraft's fuselage constantly bends and flexes under enormous pressure changes and aerodynamic forces. Although the structure is incredibly strong, years of repeated stress gradually create metal fatigue. On a white aircraft, inspectors can easily spot faint dark lines that may signal the beginning of microscopic cracks. Loose rivets, chipped paint, and slight bulges in the fuselage become far easier to detect. If the aircraft were painted black or another dark color, many of these tiny warning signs could blend into the surface, making inspection slower and more difficult. White doesn't hide problems, it exposes them.
Structural cracks are only part of the story. Some of the most dangerous problems begin inside the aircraft. Hidden within the wings and fuselage are complex hydraulic systems, lubricating oils, and high-pressure fluid lines. If a tiny leak develops anywhere in the system, those fluids begin escaping through microscopic openings. As the aircraft flies, airflow spreads the leaking fluid across the outer skin. On a white fuselage, orange hydraulic fluid, black engine oil, or other colored stains become instantly visible, even under dim airport lighting. Those stains immediately tell engineers exactly where to begin their inspection. On a dark-painted aircraft, the same leak could remain unnoticed for much longer. White paint turns even the smallest leak into an obvious warning sign, helping maintenance crews solve problems before they become serious. Another important inspection happens after nearly every flight. Engineers check for bird strikes. Although modern aircraft are built to survive these impacts, collisions with birds at hundreds of kilometers per hour can still damage the nose, wings, or engines. Sometimes the damage is obvious. Other times, it's almost impossible to see. A white aircraft makes these inspections much easier. Tiny dents, scratches, impact marks, feathers, or traces of blood immediately stand out against the bright surface. That allows technicians to quickly identify the affected area and inspect it for hidden structural damage before the aircraft returns to service. Some people claim airlines paint aircraft white to hide repair work. The truth is exactly the opposite. Every repair performed on a commercial aircraft is carefully documented and inspected under strict international aviation regulations. Paint cannot hide poor maintenance from certified inspectors. White exists for one reason: to make defects easier, not harder, to find. If white is so effective, one question still remains. Why do so many airplanes have black noses? And why are there dark panels around the cockpit windows? At first glance, it seems to contradict everything we've learned. But these black sections serve highly specialized purposes. The rounded nose cone isn't just decorative. Hidden inside is one of the aircraft's most important systems: the weather radar. This radar continuously scans the skies ahead, detecting thunderstorms, heavy rain, and dangerous weather before the pilots encounter them. Standard white paint contains titanium dioxide, a pigment that can interfere with radio waves. If the radar dome were coated with ordinary white paint, radar performance could be reduced. Instead, engineers use a special radio-transparent coating that allows radar signals to pass through with minimal interference. Historically, these specialized coatings naturally have darker colors. That's why so many aircraft noses appear black or dark gray.
The dark panels just below the cockpit windows serve another important purpose. they're not there for style. They're there to protect the pilots. At cruising altitude, sunlight reflecting off the bright white fuselage can produce intense glare directly into the cockpit. Those matte black surfaces absorb the reflected light instead of bouncing it back toward the pilot's eyes. The result is better visibility during long flights and reduced eye fatigue. So while white dominates the aircraft, these carefully placed black sections exist purely for function. They are small exceptions to a rule that has been perfected through decades of engineering. But some airlines go much further. Every now and then, you'll see aircraft painted entirely in black, bright orange, deep green, or other eye-catching colors. If white is clearly the better choice, why would any airline ignore it? The answer has everything to do with marketing, and it comes at a surprisingly high price.
Despite all the advantages of white paint, some airlines deliberately choose bold colors, from jet black aircraft to bright orange, deep green, and vivid blue liveries. These airplanes instantly capture attention wherever they land. They become social media sensations. Passengers photograph them. Aviation enthusiasts remember them. For the airline, that visibility is valuable marketing. But standing out comes at a price. Every colorful aircraft costs more to operate than its white counterpart. The darker paint absorbs far more heat, forcing cooling systems to work harder while the aircraft sits on the ground. In some of the world's hottest regions, that extra heat becomes more than just an inconvenience. It becomes an operational challenge. Airlines operating dark-colored aircraft must follow much stricter procedures during hot weather. At airports across the Middle East, Africa, and other extremely hot climates, black-painted aircraft often cannot remain parked under direct sunlight for extended periods without external cooling equipment. Without active cooling, temperatures inside the aircraft can climb rapidly toward dangerous levels. Sensitive electronics begin overheating, composite structures experience greater thermal stress, cabin temperatures become unbearable. Every additional minute on the ground increases maintenance demands and operating costs. The dramatic paint scheme may attract attention, but it also creates engineering problems that white aircraft simply don't have. Some people mistakenly believe colorful passenger aircraft are designed for camouflage or military-style visibility. That's completely false. Commercial airliners have no need for camouflage. Their enormous size makes hiding impossible. Bright liveries exist for one reason only: brand identity. They're flying advertisements. The unique colors help airlines build recognition, strengthen their image, and leave a lasting impression on travelers. From an engineering standpoint, however, colorful paint offers virtually no performance advantage. In fact, airlines willingly accept higher fuel consumption, increased maintenance costs, and stricter operating procedures simply to create a memorable visual identity. It's a business decision, not a technical one. When all the evidence is brought together, the answer becomes remarkably clear. White isn't the result of boring design. It's the result of brilliant engineering. A white aircraft reflects heat, protects advanced composite materials, reduces cooling requirements, lowers fuel consumption, makes structural damage easier to detect, reveals fluid leaks instantly, and helps maintenance crews identify hidden problems before they become dangerous. Every one of these advantages improves reliability. Every one reduces costs. And together, they help make modern aviation one of the safest forms of transportation ever created. What appears to be a simple color choice is actually the product of decades of scientific research, engineering experience, and economic optimization. The next time you're standing beside the giant windows of an airport terminal, watching dozens of nearly identical white airplanes lined up on the runway, you'll see them differently. They're not painted white because designers lacked imagination. They're white because physics won. Every layer of paint reflects sunlight away from delicate materials. Every bright surface helps engineers detect problems before they become emergencies.
Every kilogram saved reduces fuel consumption across millions of miles. Behind that simple white exterior lies one of aviation's smartest engineering decisions. One that quietly saves airlines millions of dollars, protects cutting-edge technology, and helps ensure that millions of passengers arrive safely every single day. Sometimes, the greatest innovations aren't the ones that stand out. They're the ones so effective that we stop noticing them altogether.